Now, of course, that isn't very useful in quantum mechanics. We want to know a certain region of space in which our particle is most likely to be found. So suppose that we want to describe a particle whose position is known to be within a certain localized region of space along our x-axis. How exactly do we go about producing such a localized wave? So if we take the superposition of many plane waves, each with a slightly different wavelength, and therefore each with a slightly different momentum, we can in fact obtain a single wave that is found within a localized region of space along the x-axis, and such a localized wave that is produced as a result of the superposition of many plane waves is known as the wave packet. So what exactly do we mean? So let's look at the following diagram. So in this diagram we have a red sinusoidal wave that is given by psi 1, and the blue sinusoidal wave that is given by psi 2. Now if we add these two waves, if we add our vertical displacement, we get a third wave that is known as the superposition wave. Now basically, if we add a third wave to it, a fourth wave, a fifth wave, and we continue adding waves, in fact, if we add infinitely many plane waves, then eventually we produce a single wave that is localized to a certain region. So basically, our constructive interference takes place within this region, and destructive interference takes place everything else. So basically, if we take the superposition of infinitely many plane waves, eventually we get something known as the wave packet. So this wave basically extends over the following region that is given by delta x, and this represents the uncertainty in finding our particle, our free particle, within the following region. So this basically means that our free moving particle is most likely to be found within this particular region. So basically, a wave packet is a localized wave found only within a certain region of space that consists of many superposition sinusoidal plane waves with slightly different momentum. So basically, each one of these waves, each one of these plane waves that we add up has its own unique momentum, and the momentum between any two waves differs by only a small amount. Now, since the momentum now has a range of values, that basically means there is an uncertainty in the momentum. So our delta P is no longer equal to zero, as in this case, in which the momentum was unique to this wave. So the momentum was a fixed quantity. Now, because we're adding many plane waves, the momentum of this wave won't be a specific value. It will have a certain uncertainty, and by Heisenberg's uncertainty principle, there is now a finite uncertainty in the position of our particle given by delta x. So basically, before the delta x, the uncertainty position was infinitely large, now our uncertainty is given by this value, and that basically means our particle is found somewhere within this region. So in a way, we see that the wave packet is like a wave function in that it basically represents the region of space in which our particle is most likely found. So basically, as the wave packet moves along the x-axis, our particle also moves along the x-axis, and the particle always remains within that region of space given by delta x. So let's suppose at some initial time t1, our wave packet was found within this region along the x-axis. So that means that our particle is most likely found within this region of space. Now, if our particle is moving along the x-axis, the wave packet moves along with it. Now, let's suppose at some time t2, the wave packet is found in this position. That basically means our particle is no longer found in this region, but now it's most likely found in this region. Likewise, if the wave packet then moves in this position, and then it's found here at a time t3, that basically means the particle is now most likely found within this particular section. In this lecture, we're going to examine some of the constraints that exist when we're dealing with wave functions in quantum mechanics. Now, in quantum mechanics, every single system, for example, an electron, has its own wave function associated with that system. Now, we know that the wave function is obtained by solving the Schrödinger's equation, and the wave function itself basically provides us with all the information to know about the motion and behavior of that system. Now, our system, for example, could be an electron. Now, if we know what the wave function is, which, by the way, depends on the position x as well as the time t, if we know what the wave is, what the wave function is, this gives us the single value probability amplitude of the wave produced by that system. So basically, this gives us information about the actual wave itself. It gives us the amplitude, how high or how low our wave goes. Now, what about if we take the square of the absolute value of our wave function? Well, this gives us information about the particle of that system. So basically, it gives us the probability distribution, the probability density of that particle that produces that wave. This basically tells us the probability, how likely it is that we are to find that particle in a certain position x at a certain time t. Now, for this quantity to actually make sense, it has to be between 0 and 1. We can't get a probability that is negative, and likewise, we can't get a probability that is greater than 1. So basically, in order for a wave function to be useful and physically meaningful and measurable, it must satisfy a certain set of requirements. Now, requirement number 1. So the wave function must satisfy, it must be a solution to Schrödinger's equation, to the following equation, which is basically the time-dependent Schrödinger equation. Now, what exactly do we mean by requirement 1? Well, to understand what we mean, let's recall an analogy. So, let's suppose we're dealing in classical mechanics. So we have the equation force equals mass times acceleration. So remember, in quantum mechanics, Schrödinger's equation is the analogous equation to force equals ma. So in classical mechanics, we use this equation to study the motion of our object. In quantum mechanics, we use this equation. So let's suppose that we know the force on our object is 10 newtons. Now, if we know the force is 10 newtons, that means if we plug in a value of, let's say, 1 kilogram for the mass and 2 meters per second for our acceleration, 1 times 2 does not equal 10. So, for example, 1 and 2 are not solutions to this equation. And in the same exact way, our wave function must satisfy the solution to the Schrödinger equation. That's exactly what we mean by step 1. So let's suppose our wave function does in fact satisfy requirement number 1. What else must it satisfy? So let's move on to requirement number 2. The wave function must in fact be a continuous function, and that's simply because the probability must also be a continuous value. It must range from 0 to 1 and must be a value in between. So once again, since the square of the absolute value of the wave function psi represents the probability of finding our particle at some position x and some moment in time t, and the probability itself must be a continuous value between 0 and 1, then we see that the wave function itself must also be continuous. So basically, the wave function cannot look like this. It cannot stop here and then continue upward here. It must be a continuous function like so. So let's move on to the final requirement. So the final requirement states that the wave function must in fact be normalized. So normalized is a term that basically comes from mathematics, from statistics and probability. So what exactly does it mean for a wave function to be normalized, for any equation for that matter to be normalized? So the wave function must correctly give us the probability value. That is, the probability should never exceed 1, and the probability should never be a negative quantity. More precisely, the probability of finding a particle at any one location or another should always be 1. So what exactly do we mean by that? So let's suppose we're dealing with one dimension. So we have some type of particle. Let's suppose an electron found somewhere along the x-axis, and the x-axis extends to negative infinity and positive infinity. So, and this region here is basically our wave function. So this red curve represents our wave function. Now let's choose an infinitely small distance, an infinitely small region in space along the x-axis given by the following region. Now for our wave function to actually be physically measurable, physically meaningful, if we take the square of the absolute value of the wave function and multiply by this infinitely small distance given by dx, this should give us the probability of finding our particle in this infinitely small region given by dx. Now if we slice our entire x-axis into these infinitely small regions, and then we integrate them from negative infinity to positive infinity, if we take the sum of all these probabilities, the entire probability should give us 1. This is exactly what we mean by our wave function being normalized. So basically, what exactly does it mean for the integral from negative to positive infinity of the square of the absolute value of psi be equal to 1 with respect to dx? So basically, the sum of all the probabilities along the entire x-axis, along all of space, should always be 1. It should be 100%. Now, what that basically means is we should be able to find our particle somewhere along the x-axis. It must be somewhere along the x-axis. And when we integrate all these probabilities, when we sum up all these probabilities, the probability should in fact be equal to 1. It cannot exceed it, and it cannot be anything less than 1. So let's suppose we have a rigid two-dimensional box as shown in the following diagram. So we have the right wall of the box and the left wall of the box, and these walls basically extend upward to infinity. Now the right wall of the box lies along the y-axis, and the bottom side of the box lies along the horizontal x-axis. Now because the left wall of the box coincides with the y-axis, the left corner of the box is in a position of x equals 0. On the other hand, let's suppose the right corner of the box lies in a position along the x-axis where x is equal to L. So that basically means the distance between our two corners of the box is given by L. So let's suppose we take a particle of mass m, for example an electron, and we allow that electron to only move along the bottom side of our box between these two corners of the box. Now when the particle collides with either one of these two walls of the box, a perfectly elastic collision takes place. That basically means energy as well as momentum is conserved. So once again, let's consider a particle of mass m confined to a one-dimensional rigid box with length L. So one dimension simply means our particle is moving along the bottom side of our two-dimensional rigid box. Now as mentioned, the particle can move along the width of our box, and the collisions between the two walls are perfectly elastic. Now this type of box, this type of situation is commonly known as the infinitely deep square wall potential, or simply a rigid box. So this type of situation is known as a particle moving inside a rigid box. Now for this particular situation, let's suppose that our potential of our moving particle is equal to 0 when our particle is found between these two corners of our box. So 0 is less than x, which is less than L. Now on the other hand, if our particle is found at either one of these two corners or anywhere beyond our two corners, our potential energy with respect to x, which is the y-axis, basically jumps all the way to infinity. Now the question that we want to explore in this lecture is basically the following. What exactly is the behavior and the motion of our particle as it moves between these two corners of our box? So we want to explore the motion of our particle when our particle is under this condition. So once again, what is the motion of the particle as it travels along the width of the bottom of our rigid box when our x is greater than 0 or less than L and less than L? Now basically, to determine the motion of any subatomic particle, for example our electron, we must determine the wave function. And to determine the wave function, we have to use Schrodinger's equation. Now notice that as our particle moves along the bottom part of our rigid box, the potential energy is equal to 0, and that basically means the particle does not feel any force, and that means the particle is in fact a free particle. Now, in our lecture on our discussion on free particles, we said that the solution to Schrodinger's equation for free particles is given by this formula. So the wave function that depends on x for any free particle with a potential energy of 0 is equal to a multiplied by sine of kx plus b multiplied by cosine of kx. So this is only true for all free particles that have a potential energy of 0. So basically, to determine the behavior and motion of our free particle inside the one-dimensional rigid box, we have to use this equation. So this means we must determine what the constants a and b are, as well as find the constraints on k, where k is equal to the square root of 2 multiplied by m multiplied by e divided by h bar squared. And because k depends on the energy, that basically means we have to find what the constraints are, what the requirements are for our energy of this particle moving along our rigid box. So basically, even though the potential energy is 0, this object, because it is in fact moving, must have some determine what the boundary conditions of our particle is. So by the boundary conditions, we know what the wave function value is when our particle is found at the corners of our rigid box. So we must determine what our wave function is when x equals 0 and when x equals L. Now, although we don't really know what our wave function is, we do know what the potential energy is of our particle when x is equal to 0 and x is equal to L. So at these x values, the potential energy, Q of 0, is equal to infinity. So that means the energy of our particle at the corners of our box is equal to infinity. Now this basically implies from the Schrödinger equation that if u of x is equal to infinity, this quantity must be equal to 0. So the wave function at 0 is equal to the wave function L, which is equal to 0. So if this was not true, then the product of u of x and psi of x would be some infinite value, and that basically means that the Schrödinger equation would be infinitely large, which implies that the energy, the kinetic energy of our object would also be infinitely large. And of course, that is not true. We begin by assuming that our particle has a finite amount of kinetic energy. So once again, from Schrödinger's equation, because our energy is equal to infinity at the two corners of our box, that means that the wave function at the two corners of the box is equal to 0. Now, so knowing this, let's begin by calculating what our constant B is. So we want to find what the value of the constant B is. So let's begin by assuming that x is equal to 0. So we're going to use this condition to find what B is. Now, if x is equal to 0, we know from this discussion that the wave function at the left corner of our box is equal to 0. That basically means the particle cannot be found at that position. Now, if this is in fact true, then that applies from this equation that sine of 0 is equal to a multiplied by sine of 0 plus b multiplied by cosine of 0. Now, because sine of 0 is 0 and cosine of 0 is 1, we see that sine of 0 is equal to 0 plus b multiplied by 1, which is equal to 0. And the only time this is actually true is if b is equal to 0. So we basically see from this discussion that the b value in the following equation has to be equal to 0. So now we know what b is. So now let's determine what the requirements are for the k. So what are the constraints for k? So since we know that b is equal to 0 from this discussion, that basically means that the wave function at x is equal to a multiplied by sine of kx plus b multiplied by cosine of kx, and because b is equal to 0, this goes to 0. So our wave function becomes as follows. So sine of x is equal to a multiplied by sine of kx. Now if we let our x equal to 0, now if we suppose that the particle is found at the right corner of the box, that basically means from this discussion that sine of L is equal to a multiplied by sine of KL, which is equal to 0. Now, the only time a multiplied by sine of KL is equal to 0 is when a is equal to 0 or sine of KL is equal to 0 or both are equal to 0. So basically, can a be 0? Now, if a is equal to 0, that basically means that the wave function of x at any position is always equal to 0. Now, if the wave function is always equal to 0, then the square of the wave function is always equal to 0. And since the square of the function gives us the probability of finding our electron, and if the probability is 0, that means the electron doesn't actually exist, the particle doesn't exist, which is a contradiction to our initial assumption. We assume that there is in fact a particle with mass m confined to the one-dimensional rigid box. So this basically means that since we began our assumption that particle doesn't in fact exist, a cannot equal to 0, and that means that sine of KL must equal to 0. So if a cannot be 0, and this product is equal to 0, then that means that sine of this quantity must equal to 0. Now this is only true if the inside of the sine function, so the k multiplied by L, is equal to 0, pi, 2 pi, 3 pi, 4 pi, and so on. So this basically implies that k multiplied by L, the inside of the sine function, is equal to n multiplied by pi, where n is a value 1 or 2 or 3 or 4 or 5 and so on. So basically, we neglect n equals 0, because if n equals 0, that means our wave function is also equal to 0. It's always equal to 0. So we neglect n equals 0, and n must equal to 1, 2, 3, 4, 5, and so on. Now, if we rearrange this equation and solve for k, we see that k is equal to n multiplied by pi divided by L, where once again n is equal to 1, 2, 3, 4, and so on. Now, if we continue on the left side of the board, recall that since k is equal to the square root of 2me divided by h bar squared, we can basically replace the k with n pi divided by L, as we do in the following section. Now, if we solve for our E, the energy of our particle in the rigid box, and we replace h bar with h divided by 2 pi, we get the following result. So the energy E of our particle inside the one-dimensional rigid box is equal to m squared multiplied by h squared, where h is Planck's constant, divided by 8 multiplied by m, where m is the mass of the particle, multiplied by L squared, where L is the width of that one-dimensional rigid box, and n is simply a positive integer. So what exactly does this equation actually tell us? Well, it tells us that a particle trapped inside a one-dimensional rigid box has a quantized amount of energy. So basically, this is in accordance with quantum theory of energy. Now notice that this positive n value is known as the quantum number, and we define zero potential energy as the lowest possible energy that our confined particle could have, and this represents a value of n equals 1. So notice an important byproduct of this discussion. Even if our particle has the lowest amount of energy, when our n is equal to 1, that particle is still moving along that one dimension of that rigid box. So that basically means even if the absolute temperature is at 0 kelvins, our particle, based on quantum mechanics, is still moving with some energy given by E1, so it still has some velocity. Now, the last question question that we want to ask is the following. So we found what B is, and we also just discussed what the constraints are for our K value as well as the energy. So now all that's left is to find what the A is. So from this discussion, we see that our wave function with respect to x is equal to A multiplied by sine of n pi divided by L multiplied by K multiplied by x, where the K has been replaced with this equation, where n is the quantum number of our confined particle. So how exactly are we going to solve for A? Now recall in our discussion on the constraints for wave function and normalization, we said that for a wave function to actually be physically meaningful and physically measurable, that wave function has to be normalized, and that basically means the integral from negative infinity to positive infinity of the square of the absolute value of the wave function with respect to dx must equal to 0. Now if we replace this with the following equation, this is equal to the integral from 0 to L from the left corner of the box to the right corner of the box multiplied by a squared times sine squared of n pi divided by L times x of dx, and this is equal to 1 by the concept of normalization. Now if we actually integrate this, we'll get the following result. So the left side is a squared multiplied by L divided by 2, and the right side is equal to 0. Now if we multiply both sides by 2 and we divide by L and take the square root, we get that A is equal to the square root of 2 divided by L, where L is simply our length of that box. It's the width of that box. So what exactly is the meaning of A? So A represents the amplitude of the wave function, the wave that is produced by our particle as it moves within the confined one-dimensional rigid box. So we see as our L increases, as the width of the box increases, this quantity decreases and the amplitude decreases. So as the width decreases, our amplitude will decrease, and likewise as our width decreases, the amplitude of the wave will increase. Assuming that the energy released in part B E is released in the form of a photon of light, we want to find the wavelength of that photon of light. So let's begin with part A. So in part A, we want to find something known as the zero-point energy. The zero-point energy is simply the lowest possible amount of energy that the electron can have. Now, generally speaking, the energy of our electron trapped inside a rigid box is given by this equation. So m squared multiplied by h squared divided by 8ml squared, where L is the width of our rigid box, m is the mass of that particle, h is Planck's constant, and m is the quantum number. Now, the zero-point energy represents a quantum number of n equals 1. So if we plug in n equals 1, we get h squared, so Planck's constant squared divided by 8 multiplied by the mass of the electron in kilograms multiplied by the width squared given in meters, and that gives us an energy value of about 1.51 times 10 to negative 18 joules. So now we want to move on to part B. So basically, in part B, we begin with an electron in quantum number n equals 3, and then that electron jumps to quantum number n equals 1, and a certain quantity of energy is released. We want to calculate what that quantity of energy that is released is. So let's look at the following graph. So we basically have the following infinitely deep square potential well, our rigid box, and our electron is basically moving along the following width of the bottom of our rigid box. Now the y-axis represents our energy. Notice n equals 1 is the energy of our particle with a quantum number that's n equals 1. That represents the zero-point energy. So the next discrete quantity of energy is n equals 2. That is equal to E2, and finally n equals 3 is given by E3. So our electron begins here, jumps down to here, and a certain quantity of energy is released as a result of that transition. So if we calculate what E3 is, then we can take the difference, and that will give us our answer. So let's begin by calculating E3. So E3 is equal to m squared multiplied by this quantity, and this quantity is simply equal to E1. So 3 squared, which is 9, multiplied by E1, that gives us about 1.36 times 10 to negative 17 joules. So